Hi everyone, welcome to week 6 of NOC Detailing series. I am Rajvijay, a senior design manager at True Silicon. So far we discussed about the NOC topologies, avoid deadlocks. But today we are talking about the what happens when different block of your chip works at a different speed. Yes, you are absolutely correct. Today's topic will be all about the clock domain crossing or CDC, how we keep our data safe for corruption. So let's get into it. A modern SoC is massive machine. Your AI accelerator might run at 1.5 GHz while your peripheral bridges are run at 200 MHz. They have completely asynchronous domain. When you try to pass data without protection, you run into metastability. Think of it like a relay race where two different runners sprinting at completely different speed. If a sender hands off baton at exact millisecond, the receiver block away. The baton drops. In hardware, this consideration a setup or hold violation. The flip-flop get confused. The voltage hovers between 0 and 1 and your data completely corrupted. So what's the solution? One of the solution we have like single bit control signal. We use a multi-flop synchronizer. We passing the signal through 2 or 3 back-to-back flip-flops at the destination domain. We give the metastable signal enough time to settle into a solid 1 or 0 before the rest of the logic can see it. For massive data payload, you can't use the simple synchronizer like for 512 data width or others. Instead, we use a highly optimized asynchronous FIFO. The data is safely written by the fast clock and stored into the memory array and safely read out using the slow clock. We use specialized Gray-coded pointer behind the scene to ensure the read and write logic never misinterpret the addresses. Of course, this method introduces a clock latency between master and slave. However, simply focusing on the clock count can be misleading. For instance, when crossing from 1.5 GHz master to 200 MHz slave, you are experiencing significant frequency degradation, making increasing the clock cycle both expected and necessary. At True Silicon, we spend a lot of time to perfecting our CDC for different knock ports and bridges because a single missed a clock crossing won't just slow down a chip, it will break entirely. Sometimes it can cause deadlock also. CDC bugs are notoriously hard to catch in simulation. What is your go-to tool or strategy for CDC linting? Let's talk about it on comment and make sure hit follow and we'll see you soon on next Monday.